Hello everybody. Today I want to talk to you about an ultra low cost RCL meter, resistance, capacitance and inductance. To give you an idea, this is about maybe €3 or $3 or whatever it is, the equivalent in your home country. So it is really very low cost, and as you will see, it is actually as good as some commercial expensive equipment. And that makes it very interesting, of course. This work was done by Pedro Ignacio, Rui Guerra and me, Peter Sterlinger, presenting it to you today. If you want to find more detail, because I'm going to simplify the message today very much, of course, if you want to read more detail in the software that we used, then you can go to our publication in Sensors of this year, 2022. I will link the publication below this video, or actually you can read it also here. The Department of Information Code will also directly bring you to this. So let's kick off. How does this thing work? Well, we used a normal Arduino. Probably you're familiar with this, with the platform of Arduino. It is based on the microchip AVR Atmel microprocessors, and they have become quite powerful pieces of equipment and continuing to be very cheap, actually. So what we're going to make use of today of these microprocessors is the analog digital converters, the ADC ports that are incorporated into the microprocessor. Actually, the version that we used here today has 6 of those, so also the Arduino has 6 of those ADCs. An ADC, analog digital converter, converts a voltage into a number. So, for instance, in our case, when we have from 0 to 5 volts, the ADC converts it into a number. From 0, it's 10-bit, so from 0 to 2 to the power 10 minus 1, that is 1023. So if we get the number 0 from our ADC, the voltage was 0, and if we get 1023, then the voltage was 5 volts and anything in between. Now, to give you an idea, what are the rest of the components that are used then in the Arduino platform, we have here the microchip microprocessor, that is this tiny thing here. We have here our 6 ADCs that we're going to use. We have here a voltage power supply that is then also available in these pins over here. Then we have here a communication with the USB port, and this makes it of course even more interesting, because then we can also communicate our resistance, capacitance and inductance values to the rest of the world. So to communicate this, we have this USB port, and that has to be then translated from a normal serial port, that is something like a serial port, then translated into USB by this FTDI translator, Future Technologies, if I'm not mistaken. And finally, I want to mention here that can be relevant is these 13 digital ports, and also this crystal that is used to supply the 5 megahertz reference, 5 megahertz probably, for this microprocessor. So how did we then make use of this? The main thing is to take note of these 6 ADC ports. And to talk a little bit more about these ADC ports, the original versions, or actually the original versions of these ADC ports, they were just input ports, and they had a very high input resistance of the order of 1.5 mega ohms, meaning that if you did not connect anything to this port, the value was floating, because this 1.5 mega ohm is not a good way to determine a voltage here. So it basically then was a floating input device, and that makes it then sometimes a little bit annoying, because if you didn't connect anything to it, then this port was undetermined. So most engineers actually then avoided this undetermined state by adding a pull-up resistor to it. And then the engineers at Microchip, they actually added this to their analog ports. So then you had 2 input modes. One was floating and the other one was pull-up resistance, with a pull-up resistance to 5 volts, meaning that if you did not connect anything to A, then the input voltage would be this 5 volts and you would measure a determined state. Of course, you would have to be careful when you're connecting a real signal that the output resistance of this signal was lower than this pull-up resistance from the chip. Otherwise, the 5 volts from the chip, it would win and you would always measure 5 volts. But I guess that you understand this and this is under control. Now it became even more interesting when these people at Microchip, making the AVR Atmel microprocessors, they added also the possibility to use the analog input ports as analog output. Meaning you could use them, program them, set them up as voltage sources, either 0 volts or 5 volts. And this then they become voltage sources with a certain output resistance, and this is in the order of 50 ohms. So now we have 4 modes that we can set our analog input ports up. It is floating input, we have pull-up resistor 5 volt to 5 volts pull-up resistor input, we have 0 volt output through 50 ohms output resistance, and we have 5 volts output through this 50 ohms output resistance. So these are the 4 modes, and also note that I have shown here some capacitance, which is the input capacitance of all of these ports, because don't forget that of course these are based on microchips, on electronics, and they are based on transistors, and transistors always have some capacitance. And in most cases engineers, they don't like this capacitance, but we are actually today going to make use of these capacitances. And to get you an order, to get you an idea, it's about 25 picofarad is this input capacitances. So based on these 4 modes, we can actually measure resistance, capacitance, and inductance. Let me show you how this works. So first of all, let's connect resistance to our system. So I've taken here 2 ports, A0 and A2. It is better to take 2 ports that are a little bit apart, not use A1 and A0 and A1 for instance, because then these 2 ports themselves have between themselves some stray capacitance, which of course you want to avoid. So it's better to take ports that are a little bit apart. For resistances it doesn't matter, but for capacitances it might influence your measurements, so it's better to avoid it. So we're going to use here always port A0 and A2. So first of all, we're going to put them in 0 volt output and then maybe wait a long time that everything is nice stable. We will always do this in this schemes. And then we're going to switch one of them. We're going to switch from 0 volt output mode to this pull-up input mode, meaning that now this port is connected to the 5 volts through a pull-up resistor. Now to show you how it works, I'm going to simplify the circuit shown below, but of course in reality when you want to do the calculations you have to take all the components into account, but I'm just going to show you here today to simplify it, that you will understand it, and then you will probably you can also work it out yourself if you know something about mathematics and electronics. If not, the program is available at the end on the publication. So what are we going to do? First we note that this pull-up resistor is much smaller than this output, the input resistance of this port. So we can ignore actually this input resistance. On the other side also, this output resistance that we have here is 50 ohms, is much smaller than this pull-up resistance, which was 35 kilo ohms. So to simplify it, we can also take out this one. A2 is directly connected to 0 volt. And we can also remove this one, it's connected to nothing. So basically we have these 2 resistances and the capacitances. The capacitances can also take out of the equation once they are, let's say, in steady state, when they are full. How long does it take this to adjust to the new voltages? How long does it take? That is your RC time of your circuit, tau. And in this case, considering these resistances, about 35 kilo ohms, and this value of capacitances, which was 25 picofarad, you come up with an order, let's say 1 microsecond, and that is actually faster than your microprocessor is processing, meaning about the same as a cycle of your frequency of your processor. Meaning normally when you do normal, your program is running, normally this is not something to worry about, and we're always in this, in this case, we're always in the situation that these two capacitances are charged to their final value and can thus be taken out of the equation. What we wind up with is these simple two resistances, a voltage divider, and a voltage divider is very simple to calculate. We have here 5 volts on one side, pull-up resistor, our unknown resistor in blue, and then port A2 which is connected to ground. So the voltage here is 5 volts times this unknown resistor value divided by the sum of these resistances. Or to say it in the other way around, the unknown resistor value, our load resistor, is the pull-up resistor times the ADC value divided by 1023 minus the ADC value. And to show you that it works, I have done here, I will show you here, and as you can see here, I put the resistance here. Note, there is no additional hardware connected to our Arduino. It is just plugging in the resistance in ports A0 and A2 and let the program run. So I have here the program running. I have to set it up. Yes, I have it in mode R. I will upload it. Oh, it has been somebody has been disconnected it. Serial port, I have to do USB 1. Okay, I upload it to the Arduino. Now it's uploaded. I can now see what it is giving me. It is printing me 43 kilo ohm, which is also what I measured by my multimeter. So this thing is actually working. No additional hardware, and I can measure it. Also note, the value is still a little bit, maybe you could call it noisy. I'm just taking one sample once every second. So I'm wasting a lot of time doing, the Arduino is basically doing nothing. You could use this time for using oversampling, and the quality of the signals will get actually much better. Now, this is simple. I hope you understand this. Let's take a look how capacitance can be measured. Again, we just bridge two of these ADC ports by a capacitance thing. Let me already connect it. I will take this for small capacitances and I will put it in port A0 and A2, as you can see. How does this work in this case? Well, let me show you again. First we put it 0 volt, and then we switch both sides in this case. One goes to floating input mode. So now we have this output resistance of 1.5 mega ohm. We have the input capacitance 25 picofarad, 25 picofarad on the other side because we switched to 5 volts output mode. So we have here 5 volts through the 50 ohms output resistance of this one. Now for very fast times, again we have to be faster than this, slower than this 1 microsecond, but that is normally not a problem. But we have to be actually faster than the time it takes to put charge here on pin A0. And this goes through this resistance of 1.5 mega ohm. It takes time for the charge to reach this A0. How long does it take? Well, typically about 40 microseconds. So you just have to basically immediately start measuring sampling your A0 port. In that case, what do we have? Then we can ignore this input resistance, 1.5 mega ohms here. And this one also then actually can taken out of the equation. So in a simplified version, of course in reality it's a little bit more complicated, but in a simplified version you just have, let's say, a voltage divider now based on two capacitances, or you can call it two impedances. The voltage then is voltage divider, the impedance of C pin divided by the sum of impedances. The impedance of a capacitance, as you know, is 1 divided by J omega times the capacitance. So if you do this correctly, now the voltage at A0 is this voltage divider, or in other words, your unknown, this blue capacitances, is your known capacitance times your ADC value divided by 1023 times your ADC value at port A0. Maybe you think like, now impedances, I don't know what it is, and I don't know what frequency you talk about omega that you have here. So maybe you like more to have it explained in a way of talking about charts. So this is what I've done here. So you have two capacitances, and there is no way for charge to reach here pin A0, meaning that the sum of this charge here, Q plus and Q minus on the other capacitor, don't forget capacitances are just two parallel metal plates, and the sum of this metal plate on from this capacitor plus the charge on this metal plate from this capacitor must be 0, because no charge has been able to reach there yet. So this is the boundary condition. The sum of these two charges is 0, and of course you have your typical capacitance definition, that the capacitance is per definition the charge divided by the voltage drop over the capacitance. So the charge that is here on these two here, and is this 5 volts minus the voltage at A0, and the charge on this one, this Q plus here, and this then has Q minus here. This charge here is the voltage at A0 minus 0 times capacitance. And if you do this then correctly, to solve this equation, you get again, of course, that your capacitance value is your known capacitance value times the ADC value divided by 1023 minus your ADC value. Okay, so let me show you that this works. I have here, this works for small capacitances. So what are we going to do? We're going to switch to mode float input and 5 volts output, and immediately start measuring the voltage at A0. Let me see if I can show this to you. I have to put it now at mode C small, upload the thing to the capacitance, to the Arduino, and to show you that it works. It is 310 picofarad. I think this is more or less value. It's a little bit noisy. Capacitance is always noisy, because if I put it closer, for instance, closer to my head or something like this, closer to something metal, it can actually change value, and actually sometimes it doesn't make good contact. At the end I will show you how well this thing actually works when you do it a little bit more careful than I'm doing it now here in front of the camera. And actually, as you will see, it works very, very well. But this mode only works for small capacitances and not for big ones. 300 picofarad is a small value. So we also have then a way of measuring for large capacitances. How does that work? Well, then we're going to make transient. What we're going to do, we're going to charge our unknown capacitance C through a known pull-up resistance, R pull-up, and then the time it takes to charge is then, of course, the RC time, as you know from electronics. The RC time, that is your characteristic time of charging this capacitance. So if you know your time for charging and you know your resistance value, then you know your capacitance value. Once again, I simplified the circuit. We start at 0 volts on both sides, and then we switch one side, we switch to pull-up input mode, meaning 5 volts connected through the pull-up resistance. So we basically have this situation in which we are charging the capacitance to 5 volts through a pull-up resistance. The end value of here of A2, we're now going to sample A2. A2 is actually now going to reach 5 volts with the characteristic time of tau given by R pull-up times C. To show this to you in a graphic, you can see it here. It starts at 0 volt, and then it will reach 5 volts with the characteristic time that is given by R pull-up times C. If we know tau, then we know R pull-up, then we know C. And we're going to make here use here of a funny trick, because these guys in microchip, they are actually very intelligent, because this analog port can also be used as a digital input. We can actually sample the digital value of this port, and this then gives the TTL kind of thing. It returns 0 or 1 depending on if it is above the TTL threshold or below it. And the thing is that this threshold is not very well defined. It can be 2 volts, 2.5, 3 volts, something like this. So it's not well defined. But what we're going to do, we're just going to do a digital sampling, sample this port until it goes over the TTL threshold. Then we're going to remember the time in which it happened and immediately start an analog sampling cycle. This sampling takes a long time, but how this works is these people at Microchip are very intelligent. They latch the analog voltage to a buffer and then start sampling the buffer, meaning that once we start sampling, the voltage that we will get is referenced to the beginning of our sampling and not to the end. So we will do TTL, digital sampling, until it goes over the threshold. We remember the time and then we sample the voltage. And if we know the time and the voltage, then we can, from that, we can actually determine the tau that was used in charging this capacitance. And to give you, I'm not going to bore you with the mathematics, but you can imagine then your capacitance value is the time in which it passed the TTL threshold and a logarithmic function of the ADC value at this TTL threshold. Okay, if you don't believe me that it works, I'm again going to show you, and I'm going to replace the small capacitance with an electrolytic. It's on paper it should be about 10 microfarads, but I've already measured it. It is actually just 9. Also with the commercial bridge I checked it is 9 microfarad. Once again, no additional electronics, just plugging it in, and I just have to change here my RCL meter. I have to do to see big mode and then upload it to the Arduino and then show you. Let me see if it works. Yes, 9.24 microfarad. So as you can see, this works for this also works for large capacitances. Now to continue, we can also actually measure C and R simultaneously. So show you how this works. If we're going to connect R and C in parallel to be measured in parallel, then of course we can use the same technique of transient measurement, but don't forget now at the end the final value at A2 is no longer 5 volts, but it is something lower, because at the end, when this one is charged and can be taken out of the equation, we are winding up with this voltage divider. So the final voltage is 5 volts multiplied by R divided by the sum of these two. So it will be lower. This can be for small values of R, of course. This value can become very low and this transient nearly flat. So it will start then influencing our measurement. But what we can do, we just measure this curve, determine then the final value by infinite time. We measure, we find the resistance value here at the final value of the voltage. And then based on that, we can then also, by finding the tau in this curve, we can then, as we know R and we know R pull up, then we can again determine capacitance. I'm not going to show you this because it's also more complicated here to put two components into this device, and I want to save a little bit time. I want to finish here with before I present the summary of the results. I'm going to also show to you that you can also measure inductance. So I have here an inductance, but I have to warn you before that this is not a very good device for measuring inductances. It doesn't work very well. But to show you, I put in here an inductance. Again, ports 0 and 2. We're going to do a transient, we put before the transient, we put both at 0 volt, and then we switch A2 to 5 volts, and we get now again a transient now starting from 5 volts and going down to 0. And the time constant of this transient is given by the inductance value divided by the pull-up resistance. So once again, we measure the transient, we find out when it's going below the TTL threshold, then we sample and we know the time constant tau, and if we know the time constant tau, then we know our inductance value. Once again, seeing is believing, so I'm going to show you that this works. I now have to put this into mode L, upload it to the Arduino, and show you here the output, what is showing 6.6 millihenries. I have to warn you that this is not very good. It doesn't have a very large range of measurements. What are the ranges of measurements? So let me give you here a summary of all the measurements that we can do with it. So here the measuring resistance. As you can see here, this part of the graphic is most important. That we have here the nominal resistance value. So that is the one that is the color coded, that's written on the resistor. These we've measured actually, and then what we measured by the device, by our Arduinos, and compared to a commercial Fluke multimeter. As you can see that our device is just as good as the Fluke multimeter. As you can see, actually the Fluke doesn't go beyond about 10 mega ohms, while our goes to 100 mega ohms without problem. And the lowest values we could measure was about 0.3 ohms. So we get here easily 8 orders of magnitude measuring resistances, which is not bad for a device that costs only about 3 euros and for which you can then immediately upload your values to a computer or to the internet or whatever you want to do with it. About 1 ohm to 100 mega ohms, 8 orders of magnitude, which is not bad. Actually, the range is better than this Fluke, but not significantly. Now look at the small capacitance values. As you can see, we could measure from about 10 femtofarad, and these capacitances are difficult to arrange because they have no use anywhere. 10 femtofarad, it's too small to be any useful, but it actually can measure. The Fluke actually measures and it levels off. It cannot go measure below, let's say, 0.1 nanofarad, 10 picofarad, I have to say correct, 10 picofarad. It levels off, while ours continues to 10 femtofarad. And on the other hand, it can measure here to about 10, maybe 100 nanofarad, which is, don't forget, is measuring small capacitances. And the error is not so big. You can see here the relative precision of our measurement. Actually, it is here doing better than the commercial equipment. Also, we compared it to a BK capacitance meter. Now, the next one is then the large capacitances. Our device goes to about 10 millifarad, and after that the measurements, they become very lengthy. It will take a long time to measure it. And on the lower end, as you can see here, our device, especially this Atmega, the Arduino Leonardo that we used, is getting here a little bit of less quality, it seems. The Arduino Uno, that has an Atmega 328P, that one seems to be still doing quite okay, and the Fluke and the BK are doing more or less with the same quality. For now, to summarize this all, what I've presented to you today is a very cheap RCL bridge for which you don't need any extra electronics whatsoever. No wires, no capacitances you have to connect. You just connect the thing you want to measure to the 2 ports of an Arduino, and you can measure your capacitances, inductances, and resistances. The quality is remarkably as good as a commercial equipment, not doing worse. And considering the cost, that is of course very nice for us. It's based on the AVR Atmel processors that you can find in Arduino, for instance, the Arduino platform. The methods we used is voltage division for resistances and small capacitances, and we use transient techniques for large capacitances, for inductances, and for combinations of resistance and capacitance. The ranges that we were able to do when we did it carefully, of course. What I show you today here is not done careful, but read our publication and you will see how it should be done carefully. And then you can do ranges from 0.2 ohms to 100 mega ohms about, and capacitances from 10 femtofarad to 20 millifarad we managed to do. Inductances from 0.4 millihenry to 2.7 henries. And the ranges of combinations of R and C, it depends a little bit. I cannot say this directly like this because of when you measure, for instance, a small resistance value, then you're no longer able to correctly measure capacitances. And vice versa. If you have large capacitances, then it's very difficult to measure reasonable resistance values. So the range is, in principle, it goes the full range of this, but you will lose a little bit quality in your measurements. Also, finally, to mention is that it's important that you have a good stable power supply, because the more noisy it is, of course, the less quality you will get in your measurements. So I hope this was useful for you, that you can actually have a multimeter connected to the internet, connected to the computer for very low price, and actually very simple to operate, no extra electronics necessary, and then it becomes a very versatile tool. If you want to get more information, please read our paper, which I will link below. And if you want to see the code used for measuring, the quality code, then also please go to this to our publication, or follow this link that is written here now on this page here. I hope this was useful for you, and thank you for your attention.